Okay, I just want to take a quick second and go through a few problems in this worksheet just to acclimate you to what the worksheet is going through. It's self-guided, so it tells you what you need to do for each step. So it tells you what a molecular formula needs to include, and that's the chemical symbol, the subscript as well. So we gave the example of H2O in class, which has 2 hydrogen atoms, which we know from that subscript, and 1 oxygen atom, which we said we know because there's no subscript on that oxygen. So we go through finding molecular formulas and then taking those formulas and turning them into molecular or molar masses. Molecular mass and molar mass are the same thing. You can refer to them in the same way. And so that's what this worksheet is going to walk us through. So the first thing it asks us to do is to write the molecular formulas for each of the molecules that are shown here. Now, I want to do one example from each of these different sections just so you know what's expected. So let's look at this second problem right here. So in the first one that was done for us, we see that there's 1 carbon and 2 oxygens, which is what my molecular formula says here. I have carbon, there's no subscript because there's only 1. I have oxygen, and it has a subscript of 2 because there's 2 of them. In my second problem, we then want to count up all the different elements that we have, which are going to be carbon, oxygen, and hydrogen. Okay, and we are going to put that into our molecular formula. So this is going to be carbon. Carbon always comes first. We always show carbon first. So there's 2 carbons, so C2. Then we do hydrogen. When you have a carbon first in your formula, the hydrogen will always come second. So we have hydrogen here next, and there's 1, 2, 3, 4 hydrogens, so C2H4. And our last element is oxygen, which we have 1, 2 of. So our molecular formula is C2H4O2. Now, there are generalized rules for what order you need to put the elements in when writing out the molecular formulas, but since we are just learning how to write molecular formulas, I will not penalize you if you put them in the wrong order. Okay, sometimes you can put them in different orders, and that's totally fine. We sometimes see molecules that are the same, that have their molecular formulas written differently, even on the internet, in textbooks, in published papers, and everything like that. So I don't hold it to a specific standard. What I care more about is that you are able to use that molecular formula to calculate the molar mass or the molecular mass. Again, those are the same thing. Molar mass, molecular mass, they're the same thing. So you can use them interchangeably. So the molar mass of a compound is the sum of the molar masses of all of the atoms in that molecule. So our example is that C2H4O2 from here up above. Okay, and we said that there are 2 atoms of carbon, 4 atoms of hydrogen, and 2 atoms of oxygen. So for each of those elements, we're going to take its molar mass, which we get from the periodic table, and we are going to multiply it by the number of atoms there are of that element in that molecule. So for carbon, we'll take 12.01 and we'll multiply it by 2, and that's how we get the 24.02 grams per mole. Since this is molar mass, we do need to put it in grams per mole. Okay, molar, moles, we have to show it in that form. If you were talking about a single molecule of C2H4O2, then it would be in units of AMUs, because we would be talking about individual atoms in that one singular molecule. But what we are doing here right now is talking about molar masses, larger scale type things, so we want to use grams per mole. So the next thing goes for hydrogen. Again, we get that 1.01 from the periodic table. We know that there's 4 of them, so we multiply the molar mass by 4 and we get 4.04. And the same thing for oxygen, 15.99 is going to be multiplied both by those two atoms, and you get 31.98 grams per mole. Once you have the individual masses for all of the atoms involved, you then just add them up together, and that's how we get a molar mass of 60.04 grams per mole for the molecule C2H4O2. So let's do another example. We'll do CaCO3. Now what I want to point out is how these letters are capitalized or not capitalized. So Ca is one element, and we know that because one letter is capitalized and the second letter is not. Okay? For C and O3, the C and the oxygen, the C and the O, I should say, the C and the O are both capitalized, meaning that this is carbon and this is oxygen. It is not C lowercase o, which is cobalt. Okay, so please, this is not that. It is not cobalt. So you got to be careful on what's capitalized and what is not. That is not a typo. That is in fact carbon and oxygen. So we know that this molecule has one calcium, Ca is calcium. It has one carbon and 3 oxygens. So Ca has a molar mass of 40.08 grams per mole. There's only one of them, so I don't need to multiply by anything. We have carbon. There's only one of those, so we just use its molar mass of 12.01 grams per mole. And then oxygen, there's 3 of them, so we take that 15.99 grams per mole and we multiply that by 3. And that is going to give us a molar mass for CaCO3 of 100.09 grams per mole. Okay, so when you do the rest of these problems, you want to make sure that you are first looking at the individual elements, making sure you're noting the capitalized letters and the not capitalized letters so that you find the correct element on the periodic table. Once you find the element, use its molar mass and multiply it by however many atoms there are of that element in the molecule itself. Okay, another way you may see molecular formulas expressed are with parentheses, okay? And we use parentheses when whatever is in the parentheses are portions of a molecule that are meant to stick together. And we'll learn more about that in later chapters when we start to talk about, naming of specific compounds and how we go about that, but we're not going to worry about that right now. What we want to focus on is specifically how to distribute any subscripts into those parentheses so that we know how many atoms of those specific elements there are in that compound. Okay, so the example I have here is BOH3. Now, the 3 is on the outside of the parentheses, meaning that that 3 applies to the oxygen as well as the hydrogen. It does not apply to the B, to the boron, because the boron is outside of the parentheses. So just like you would see in a math equation when you have an exponent outside of the parentheses, it only applies to whatever variables or numbers that are in the parentheses. It's the same thing here. So you have to distribute it accordingly. So in this molecule, we have one boron atom, but we have 3 oxygen atoms and 3 hydrogen atoms, because that 3, again, that 3 outside the parentheses was distributed in to the OHs, okay, to the oxygen and the hydrogen. Another way to think about this is if you were to visualize this molecule, there would be a boron, and then it's saying that there are 3 of these units because whatever's in the parentheses wants to stick together. So we can then visualize our 1 boron, our 3 oxygens, and 3 hydrogens. Okay, so because whatever's in the parentheses wants to stay together, we can visualize those as individual units multiplied by whatever value that is on the outside of the parentheses. So let's do one of these practice problems here. So we have Sc2SO4 3. So this 3 is going to distribute into the sulfur as well as to the 4 oxygens. Now here's a case where we have a subscript and another subscript. Okay, so let's visualize what this means. This means that I have SO4 that's going to stick together, and I have 3 of these that are in my molecule. Okay, I also have 2 SCs. Okay, again, let's take note of, oops, where are you going? Let's take note of what's capitalized and uncapitalized here. So this is SC for scandium, not sulfur carbon. So just be aware of that. Okay, so we have 3 SO4s, okay, meaning that then gives us 1, 2, 3 sulfurs. Here, we'll ignore this one for a second. I have sulfurs, there are 3 sulfur atoms. Oxygen, there's 4, 8, 12 atoms. And then SC, there's 2. Okay, so this is 3 atoms because we did 1 times 3 when I distribute that 3 in. Oxygen is now going to be 4 times 3 when I distribute that 3 in to the parentheses. Okay, so we now know how many sulfur atoms, oxygen atoms, and scandium atoms we have. We find their molar masses from periodic table. Okay, and you should get a molar mass of 378.10 grams per mole. Okay, now another way to check yourself when you're doing these problems on your own, when you're just practicing, you can always consult the internet to see if you got the value correct. Okay, the internet can always be your help in that way. What I don't want you to do is just look up all of these molar masses on the internet right away and put the numbers in, because that's not going to help you on an assessment or in the future when you're asked to find a molar mass for a specific problem where you need to then use it for other mathematical processes. We can't always look up the molar masses, okay? But you can, in these cases, as we're learning how to do this, check your work, okay, using the internet as a way to do that. Okay, so we talked about molar masses, we talked about molecular formulas, and now we want to talk about how those values, how those molar masses can be used as conversion factors. Okay, molar mass has units of grams per 1 mole, meaning we can use it as a conversion factor in the same way we do if we wanted to convert between inches and centimeters, or milliliters and liters. Okay, when we want to go from one type of unit to another type of unit, we have to use a conversion factor. So we are going to use our molar masses as those conversion factors. So the first problem, the first set of problems asks us to calculate the mass of each compound starting from moles. So our setup here is telling us to start with moles and then multiply by the molar mass, which would be whatever that mass is, divided by 1 mole, okay? So that's your grams per mole, because what's going to happen is moles are going to cancel out top and bottom, and you are going to be left with grams on the top, which are the units that you want in this problem. So it's a one-step conversion. So we are going to take our Sc2SO4 3 that we just calculated the molar mass for. We are going to take that, and we are going to find the number of grams that there are in 0.0146 moles. So we take 0.0146 moles, SC2, parenthesis, SO4, 3. And I'm going to take that molar mass that I just calculated, which was 378.10 grams per 1 mole, SC2, SO4, 3. Okay, so then we're going to multiply right across, and we are going to get 5.52 grams SC2, SO4, 3. Now I want to make a note about sig figs. When we are talking about molar mass, when you are calculating molar mass of just a compound, you do not want to use any of our sig figs rules. So do not use sig fig rules. Okay, so up here when we were adding all of these values together, okay, now our addition subtraction rules can get us to that place, but there are some cases where the rules will then mess up our molar masses. So what I want you to do is to just leave 2 to 3 decimals at the end of all of your molar masses that you end up calculating. Okay, so 2 or 3 decimals like I showed here, 2 decimals here, I have 2 decimals in 100.09 and the 378.10. Leave 2 or 3 decimals at the end of your molar mass, because really what this molar mass isn't showing is all the additional digits that we aren't seeing on the periodic table that we know are there. Okay, so molar masses, whether that's of individual elements or of the molecules, are just like conversion factors, where they can be seen as having infinite number of significant figures. So instead of writing 800 decimal places when we're trying to find a molar mass, we're just going to keep it to 2 to 3 decimal places. Now, when we're doing problems with molar mass, okay, that's when we want to use our multiplication and division sig figs. Okay, when we're using molar mass we're converting, we are automatically going to be multiplying and dividing, so we're going to be using our multiplication, division, sig figs rules, but we only reference the number in the problem, not the molar mass. Again, because molar mass is a conversion factor. And just like we talked about in chapter 1, we don't look at conversion factors for our significant figures. So we look at whatever the number is in the problem itself. So in this problem, there's 3 sig figs from the point 0.0146, 3 sig figs. Okay, meaning our final answer has to have 3 sig figs. Okay. Regardless of how big or small our molar mass is, no matter how many decimal places it is a conversion factor. It has unlimited significant figures overall. So we are going to go strictly off of the number that is in the problem that we are looking at. Okay, so our next step is to now work backwards. Okay, so we want to start, what we want to do is convert grams back to moles. I want to find how many moles are in a specific mass of an element or a compound. Okay, so in this case we're going to look at our compounds again. So we need to take our mass in grams. It has to be in grams because our molar mass is in units of grams. And now instead of multiplying by our molar mass, we're going to divide by it. Okay, and that's so that grams cancel top and bottom and we're left with moles on the top, because that's the value we are calculating. We are calculating the number of moles. So I want to do our problem down here, question C, where we're taking the CaCO3 that we calculated on the previous page. Okay, we have to do 2 conversions here because the mass we are given is in kilograms. We cannot take that kilograms and immediately convert it to moles with our molar mass because our units won't cancel appropriately. So what we need to do is go kilograms to grams, and then from grams to moles. So we are going to start with 0.125 kilograms. We're going to convert that to grams using our prefix conversion factor, where there are 1,000 grams in 1 kilogram. Okay, so that's going to cancel out our kilograms, and now we're in grams. So we've gotten to here, and now to go from grams to moles, we need to use our molar mass. So our molar mass of CaCO3 from our previous page was 100.09 grams. That 100.09 grams is going to go on the bottom so that it cancels out with the grams on top, and we're left with 1 mole of CaCO3 on the top. Okay, so we're left with moles there. So all of our units cancel. We do that multiplication and division, and with rounding and sig figs, we get 1.25 moles of CaCO3. Okay, so again, we have 3 sig figs in our original number, meaning our final answer needs to have 3 sig figs. We ignore our molar mass when we're looking at sig figs. The final part of what we're going to do in this worksheet is we are going to convert moles to molecules. Okay, so we're going to use Avogadro's number, which is 6.022 times 10 to the 23 items, whether that's moles, whether that's atoms, molecules, ions, potatoes, whatever they are. Okay, whatever the problem defines as the item that we want to find the number of, that's what we use as our unit for Avogadro's number. So here we are finding the number of molecules of our compound. Okay, so we are going to take the mole values that we calculated from this above problem, so from A, B, and C, and we are going to use that in this problem. So let's start with our 1.25 moles of CaCO3. Okay, so as our example shows us when we're starting with moles, we then need to multiply by molecules so that our moles cancel out appropriately. So we're going to take Avogadro's number, which is 6.022 times 10 to the 23 molecules. Divide that by 1 mole. And we're going to multiply right across to get 2.51 times 10 to the 23 molecules of CO. Oops, hold on, I'm looking at the wrong problem. One moment. We get 7.53 times 10 to the 23rd molecules of CaCO3. Apologies, I was looking at the wrong answer for that one. So all we do is take our mole value, we multiply it by Avogadro's number, and that's how we get our molecules. And you'll notice that whenever we do this, nothing about the specific molecule is relevant to this conversion. Okay, so this could be 1.25 moles of oxygen, okay, and we would get the same number out because this conversion factor does not utilize the mass or the identity of the compound itself in order to get the answer, because Avogadro's number is a counting number. You're going to have 5 pieces of candy in the same way you're going to have 5 people. There's going to be 5 things for you to count regardless of what they actually are. And the same still applies, so this is a counting number. Okay, so every time that you have something that's 1.25 moles of whatever it is, if you convert it to molecules, it'll always be 7.53 times 10 to the 23 molecules of whatever it is you're counting. Okay, so now that I've shown you an example from each section, go back through your own worksheet, prove the math that we did together, prove that to yourself, double check the math, and then go through the remainder of the examples that I have in this worksheet for you to complete.